This banana is actively producing antimatter. This might seem like an absurd claim considering that antimatter is the single most valuable substance in existence, worth an estimated $62 trillion per gram. And yet, it is completely true. Also, this banana is not the only thing that produces antimatter, as you can also use modern scientific equipment such as this RadiaCode 110 device to prospect for antimatter producing minerals as well. All of this is due to a quirk of both physics and geology. How? Well, when radioactive decay of an atom occurs, there are multiple different processes that can occur depending on the isotope in question. The most common of these decay methods are as follows. Alpha decay, which releases the helium atom, gamma decay, where an excited nucleus releases excess energy as a gamma-ray photon to reach a more stable state, and beta minus decay, where an unstable nucleus as a whole becomes more stable by decaying into a different isotope, thus changing a neutron into a proton while also releasing an electron and an antineutrino. Yet, there is a very specific radioactive decay type that produces antimatter, specifically beta plus decay. During beta plus decay, an unstable nucleus as a whole becomes more stable by decaying into a different isotope, thus changing a proton into a neutron, while also releasing a neutrino and a positron. Since a positron is the antimatter counterpart of an electron, a positron will join a free electron and begin rapidly circling each other, forming what is known as positronium. Then, the two particles quickly and violently collide and annihilate each other, converting both of their masses entirely into energy, releasing typically two photons that fly out in opposite directions of each other, thus creating gamma rays. And all of this occurs in less than 200 nanoseconds or 1/5 millionth of a second, which is why you will never be able to see the antimatter which is generated. Regardless of the isotope this begins with or results in, the released energy is always the same, creating what is known as annihilation radiation. This can be and is picked up by devices such as the RadiaCode device by specifically looking for measurements of 511 kiloelectron volts. You can see detections of such right here showing the results of leaving a bunch of samples of the mineral amazonite next to the device for a full 2 hours. But why so long? Well, the isotope that I am attempting to measure antimatter generation from is potassium-40, hence the mineral in question. It just so happens that the chance of this decaying via positron emission, also known as beta plus decay, is around 1 in 100,000. Thus, it takes a while to get multiple detections of such. If you are wondering, the grouping of bananas also showed trace amounts of antimatter generation because they too contain harmless levels of potassium, of which 1 in 8,547 atoms is naturally in the form of potassium-40. Before I continue, I would like to thank this video's sponsor RadiaCode, which made it possible for me to detect the very tiny amount of antimatter reactions my bananas and amazonite produced. RadiaCode is a company which produces affordable yet highly effective smart and portable Geiger counters and spectrometers, perfect for curious minds. These devices not only allow you to measure the amount of radiation in an area such as a home, worksite, mine, or from a mineral specimen, but also visualize for yourself what isotopes are creating it via free mobile and desktop app. RadiaCode devices let you visualize the energy lines of incoming gamma rays and explore natural sources such as, but not limited to, uranium, thorium, potassium, lithium, and the radon-associated decay chain. I personally use their 110 model shown here to both prospect for radioactive mineral deposits and test which rock samples that I have in my collection are radioactive. It is so much fun seeing what isotopes are present in each specimen. All you need to do is turn on the device and look for specific emission line peaks. And now is the perfect time to buy, as seasonal and holiday discounts are currently available on the website. Simply visit the link shown on screen and mentioned in the video description, or even buy it through Amazon using this link that is also mentioned in the description below. If you are wondering exactly how much radioactivity a banana has and thus want to determine how much antimatter it produces, the answer is 15 becquerels. This translates to 15 atomic decays per second, an absurdly small number considering the average banana contains more than 1 septillion atoms. However, this is only occurring from potassium-40, which composes a minority of the banana. Assuming that 1 in 100,000 of these decays involves beta plus decay which emits a positron, that means that only a single positron is produced for a banana every approximately 1 hour and 51 minutes. So you aren't getting rich from this even if you were to somehow find a way to cheaply stabilize all of the generated antimatter in question. Bananas each only contain 0.4 grams of potassium, meaning they are only about 0.34% potassium by weight, while the mineral microcline, of which amazonite is a subvariety, is 14.05% by weight potassium. And since these amazonite samples are far more dense than a banana, is exactly why I use them to measure multiple dozen annihilation reactions. So, why isn't beta plus decay and its antimatter producing capabilities better known by the general public? In my opinion, the answer relates to its rarity, at least among naturally occurring and not lab-produced isotopes. To show you exactly what I mean, here is the distribution of known isotopes and their most common radioactive decay methods. Remember that the atomic number of each element is determined by the number of protons it contains in the nucleus of an atom. Atoms that have too many neutrons can sometimes undergo beta minus decay, while atoms with too many protons can sometimes undergo beta plus decay, meaning that this process doesn't occur in every unstable isotope. As a result, if you remove isotopes that don't naturally occur on Earth and have a half-life longer than 20 minutes but less than 1 trillion years, thousands of isotopes are narrowed down to only 7. Specifically, these 7 isotopes consisting of 1 isotope each of lanthanum, niobium, potassium, nickel, aluminum, sodium, and fluorine. Of these, there are honestly only 2 isotopes that if you had a solid 1 centimeter elemental cube of, you'd actually be able to eventually detect annihilation reactions from. The best source to detect antimatter reactions from radioactive decay would thus be from lanthanum, a rare earth element. I hope that you found this somewhat different science video interesting. A special thanks once again to RadiaCode for sponsoring this video.